Hello students, welcome to EPG Pathshala. I'm Dr. Kajal Jindal from University of Delhi. Today we are going to discuss about the module Anisotropy in Magnetic Films from the paper Thin Film Science and Technology. So students, let us see what we are going to learn in this module. In this module, the origin of the magnetic anisotropy in thin films is explained. Magnetic dipolar anisotropy, which is also known as shape anisotropy, magneto-crystalline anisotropy, magnetoelastic anisotropy are discussed. Experimental techniques for the determination of magnetic anisotropy are demonstrated. The two methods for magnetic anisotropy determination, one is the magnetometric measurements and secondly the magneto-optical Kerr effect, which is Moog measurements, are discussed in detail in the module. Magnetic anisotropy is recognized as the directional dependence of the magnetic properties in a magnetic material. It is considered as one of the most crucial parameters of ferromagnetic materials. It decides the extent of magnetization that can be achieved in a material. Basically, single crystal ferromagnetic materials possess directional magnetization properties, that is, easy and hard directions of magnetization. This is attributed on the basis of the energy which is needed to magnetize a material in the direction of externally applied field with respect to the crystal axis. Depending upon the type of application, materials with a high, medium or low magnitude of magnetic anisotropy are employed for respective applications like permanent magnets, magnetic recording, information storage media, or magnetic cores in transformers. It has been observed that the physical basis which dictate the preferred orientation of magnetic movements in magnetic thin films and multilayer structures can be fairly different from the factors that are responsible for the easy axial alignment along the symmetry direction in a bulk material. The presence of significant symmetry breaking elements in films such as planar interfaces and surfaces modify the basis of magnetization in bulks and films. The thicknesses of individual layers in a multi-layered system can be varied to modify the magnetic anisotropy of the system. The effective magnetic anisotropy energy, K, in units of joule per meter cube, which is shortly termed as MAE, can be written as the sum of volume contribution, that is kV, in units of joule per meter cube, and contribution from the interfaces, that is Ks, in units of joule per meter square, and can be expressed as follows. K is equal to K effective equals kV plus 2 times Ks divided by T. This equation gives an effective magnetic anisotropy energy value taking into consideration the interface atoms and the inner atoms of a magnetic thin film structure of thickness G. The above equation is written under the consideration that Ks divided by D, where D represents the thickness of a monolayer, is the difference between the anisotropy of interfacial atoms with respect to bulk or inner atoms. Secondly, the thin film structure is considered to be bounded on both sides by two identical interfaces. Therefore, a prefactor of 2 has been added. Let us take up an example where we will study the magnetic anisotropy determination in cobalt or palladium thin film multilayers. Equation 1, as discussed before, is generally employed in experimental studies on magnetic systems, and the determination of volume and surface contributions, that is, Kv and Ks, can be obtained by plotting the product of K effective and T versus T. Figure 1 demonstrates a typical plot for cobalt and palladium multilayers for the determination of volume and surface contributions in Ma. The intercept on vertical axis represents twice the interface anisotropy, whereas the volume contribution is given by the slope. A positive value of K effective denotes a preferred direction of the magnetization normal to the plane of thin film. A negative slope signifies a negative volume anisotropy Kv, which favors an in-plane magnetization, whereas the intercept at zero thickness of cobalt shows a positive interface anisotropy Ks, which favors perpendicular magnetization. Lower than a certain thickness, T perpendicular, which equals minus 2 times Ks by Kv, the effect of interface anisotropy overshadows the volume contribution, thus giving rise to a perpendicularly magnetized system. We will now discuss the origin of the magnetic anisotropy in thin films. Magnetic anisotropy in magnetic thin films arises primarily due to the magnetic dipole interactions and the spin-orbit interactions. The dipolar interaction, which is a long-range interaction in a system, is strongly dependent on the shape and dimensions of the sample, and this makes a significant contribution in defining the anisotropy of a system. It is of certain importance in case of thin films and is also responsible for the in-plane magnetization. In the absence of any spin orbit and dipolar interactions, the total energy of the electron spin system has no dependence on the direction of magnetization. The spins are pictured to be coupled via spin-orbit interaction with the orbits, which in turn are influenced by the crystal lattice of the material. Therefore, the total energy of the magnetic systems depends on the orientation of the magnetization with respect to the crystalline axis, and which reflects the symmetry of crystal. This is called the magnetocrystalline contribution to the anisotropy. In concurrence with the overlapping wave functions of neighboring atoms, the effect of spin-orbit interaction too contributes towards a magnetoelastic or magnetostrictive anisotropy observed in a strange magnetic system. Such a situation is generally found in multi-layered thin film systems due to the lattice mismatch between the alternate layers. Let us now study the magnetic dipolar anisotropy, which is also known as shape anisotropy. Long-range magnetic dipolar interaction, which is predominant over the outer boundaries of the sample, is one of the most important sources of the magnetic anisotropy in magnetic thin film samples. Overlooking the discrete nature of matter, the dipolar interaction in ellipsoidal ferromagnetic samples due to their shapes can be described using an anisotropic demagnetizing field, which is Hd, and expressed as Hd is equal to minus n into m, where m represents the magnetization vector and capital N is the demagnetizing tensor, which is shape dependent. In the case of a thin film, all the tensor elements are zero except for the direction normal to the surface layer. Therefore, n perpendicular is equal to 1. The magnetostatic energy can be given by the expression Ed is equal to minus mu naught divided by 2V into the integral over m into Hd into dV, where mu naught represents the permeability of vacuum. The anisotropy energy contribution per unit volume V of the system is given by Ed is equal to 1 by 2 into mu naught into ms square cos square theta. In the above expression, the magnetization has been presumed to be uniform with the magnitude equal to the saturation magnetization ms and subtends an angle theta with respect to the film normal. We will now discuss the magnetocrystalline anisotropy. The microscopic origin of the magnetocrystalline in a magnetic material is the spin-orbit interaction. Technically, the exchange interaction and the dipolar interaction could also contribute towards the magnetocrystalline anisotropy in magnetic materials. However, the exchange interaction cannot contribute to the anisotropy since it is directly proportional to the scalar product of the spin vectors and is thus independent of the angle between the spins and the crystal axis. On the other hand, the dipolar interaction energy does depend on the orientation of the magnetization relative to the crystal axis. Let us now take up the magnetoelastic anisotropy. Strain developed in a ferromagnetic material changes the magnetocrystalline anisotropy and it may thus alter the magnetization direction. It is the inverse effect of magnetostriction where the sample dimensions get altered if the magnetization direction is changed. For an elastically isotropic medium with isotropic magnetostriction, the energy per unit volume associated with this effect can be expressed as EME is equal to minus KME into cos square theta, with KME equals minus 3 by 2 into lambda into sigma, which equals minus 3 by 2 into lambda into E into epsilon. Here, sigma represents the stress developed in the material, which in turn is related to the strain via the elastic modulus E and is expressed as sigma is equal to E. The magnetostriction constant lambda depends on the orientation of magnetization and can be either negative or positive. The angle theta denotes the direction of the magnetization with respect to the direction of uniform stress in the film. If the strain in the film is finite, the effective anisotropy is primarily due to magneto-elastic coupling. Strain in thin films can be induced due to various reasons. Amongst the non-causes, thermal strain induces due to the difference in coefficient of thermal expansion. Intrinsic strain brought about by the nature of the deposition process and strain due to non-matching lattice parameters of adjacent layers. Let us now study the experimental techniques for the determination of magnetic anisotropy. Magnetic anisotropy in films or multilayers can be determined either from the static or dynamical response of the thin films or multilayered systems or magnetic systems. The dynamical response of the magnetic thin films or multilayers can be studied using ferromagnetic resonance, that is FMR, and brilliant light scattering, which is BLS. However, most of the experimental data on magnetic samples has been obtained using static measurements. Particularly, magnetization and torque measurements are frequently used to estimate the magnetic anisotropy in samples. Two of the most commonly employed techniques for magnetic anisotropy measurements are briefly discussed as follows. We will now study the magnetometric measurements. The magnetic anisotropy in samples is most commonly determined from magnetometric measurement tools like VSM or SQUID across two orthogonal directions of the magnetic field with respect to the sample surface. The angle-dependent part of the energy E of the magnetization of thin film is expressed as E equals within the brackets minus Ki plus 1 by 2 into mu naught ms square brackets close into cos square theta minus mu naught ms into h into cos of phi minus theta. Here, Ki represents all the first order anisotropy energy contributions which are intrinsic except the shape anisotropy or magnetostatic energy contribution, which is given as 1 by 2 into mu naught ms square in the case of saturated film. The last term denotes the interaction between the externally applied field and the resultant magnetization, whereas the angles subtended by the magnetization and the field and the film normal are given by theta and phi respectively. The minimization of energy as a function of the applied field H yields the field dependence of the equilibrium angle theta equilibrium, which is a function of H, and the field component of the magnetization, which is expressed as M is equal to ms into cos of theta equilibrium minus phi. Thus, Depending on the ease of magnetization, different cases are possible. First, the samples which possess an in-plane easy axis such that K effective equals Ki minus 1 by 2 into mu naught ms square is less than 0. The above mentioned procedure results in the magnetization curves which are shown in figure 2a. The area enclosed between the two curves clearly equals the effective MAE, which is K effective. Secondly, in the case of samples with a perpendicular easy axis, K effective will be greater than 0. For samples with very small domains, the magnetostatic interaction between the domains is such that the magnetostatic term can be described by half of mu naught into m perpendicular square, with m perpendicular the average perpendicular component of the magnetization. The perpendicular magnetization curve can then be obtained by minimizing E equals 1 by 2 into mu naught into m perpendicular square minus mu naught into m perpendicular h with respect to the magnetization. Here, the minus ki cos square theta term being constant, that is, the magnetization either points up, which is theta is equal to 0, or down, which is theta is equal to pi in perpendicular applied fields with k effective greater than 0 is omitted. Setting del E by del m perpendicular equals 0 yields m perpendicular equals h, giving rise to a non-zero saturation field. For in-plane applied fields, 1 by 2 mu naught into m perpendicular square is always 0, and the magnetization curve is obtained by minimization of minus ki into cos square theta minus mu naught into ms into h into cos of pi by 2 minus theta with respect to theta. The resulting curves are shown in figure 2b. In this case, the saturation fields have no direct relation to K effective. Nevertheless, the area between the curves still represents the effective MAE, K effective, including the shape anisotropy. We next consider the third case where in samples with very large domains, the effect of the interaction amongst the domains is insignificant. At h is equal to 0, although the average perpendicular component of the magnetization is 0, the magnetostatic energy term is correctly described as in equation 6 for both perpendicular and in-plane applied fields. When magnetizing the layer perpendicularly, the magnetostatic energy does not have to be overcome. Minimization of equation 6 therefore gives a perpendicular curve which is saturating immediately and an in-plane curve saturating at the field 2ki divided by mu naught ms minus ms or 2 times k effective by mu naught ms, which can be seen in figure 2c. As in the previous cases, the area between the in-plane and perpendicular magnetization curve gives the effective MAE, K effective, including the shape anisotropy energy. Let's now take up the magneto-optical Kerr effect or Moog measurements. Magneto-optical Kerr effect is a well-established experimental tool to study the magnetization in materials. It describes the change in the polarization state of light induced as a result of reflection at the surface of magnetic materials. There are two optical effects. One is the rotation of the plane of linear polarization, which is also known as the Kerr rotation. And secondly, a change of the ellipticity of the light, that is the Kerr ellipticity. Both the effects arise due to the difference in the complex Fresnel reflection coefficients for left and right circularly polarized light. The optical anisotropy can only be observed for non-zero magnetization samples, where its magnitude is determined by the off-diagonal terms of the permittivity tensor, which are odd linear functions of the magnetization. Although no direct information can be obtained regarding the absolute magnitude of the magnetization, the angle of Kerr rotation is directly proportional to the magnetization. In addition, since the magnetization is only monitored in that region of the sample which is illuminated by a focused light beam, a localized analysis of magnetic behavior can be carried out. In polar Kerr effect measurements, the light beam is made incident normal to the sample, and the field is applied perpendicular to the plane of sample. The Kerr rotation and the ellipticity in this geometry are proportional to the perpendicular component of the magnetization. For samples with an in-plane easy axis, one obtains a linear increase of the magnetization and thus of the Kerr signal up to saturation. So students, let us now summarize what we have learned in this module. First, in this module, the concept of anisotropy in ferromagnetic materials has been introduced, especially for magnetic thin films or multi-layered systems. Secondly, the various sources of magnetic anisotropy in thin film samples have been briefly discussed. Then, the two characterization techniques, that is magnetometric and MOC, for experimental determination of magnetic anisotropy in thin films have also been described. Thank you students for your attention.